Hello everyone, my name is Zhuangbin Chen from the Chinese University of Hong Kong. Today I will present our paper entitled Towards Intelligent Incident Management, Why We Need It and How We Make It. This is a joint work with Microsoft Research, Microsoft Azure, the University of Newcastle, and Fudan University. The agenda is shown below. First, I will give an overview about cloud incident management and then introduce the motivation and methodology of this work. It is followed by the characteristics of incident tickets. Next, I will talk about the key challenges of incident management and our understanding about them. Finally, I will introduce our AIOps framework called BRAIN, which aims to facilitate the management of incidents. So let's first take a look at cloud incident management. Reliability is very important for cloud enterprises. State-of-the-art cloud reliability has achieved 5 to 6 nines availability. These cloud systems are of high degree of automation. For example, more than 95% of failures can be automatically detected within minutes, and most of them can be quickly assigned to the correct service teams. Also, many services have tailored monitoring and diagnosis tools. However, cloud reliability issues still exist. 3 industry-leading cloud vendors all suffer from it. Particularly, tough incidents and outages still take a long time for mitigation. Service incidents are interruption or performance degradation of a cloud component, such as service and device. Outages are critical incidents with widespread impact, whose cost could be $70,000 per minute. Therefore, we should continue pursuing better cloud reliability. To build more reliable cloud systems, incident management plays an important role, which generally consists of the following 3 steps. The first step is incident reporting, which is to detect unusual system behaviors and render a ticket to record relevant information. Particularly, incidents can be created manually by engineers or automatically by monitors. The second step is incident triage, which is to engage the responsible service team for proper investigation. However, the assigned teams may find it is not their problem, but some troubles in other services. In this case, they will transfer the incident to other teams. The final step is incident mitigation. It is the process of bringing problematic services back to normal. In reality, minutes of service downtime could cause huge revenue loss. Therefore, some temporary workarounds will be applied first. For example, server rebooting and services redeployment. The fix to the root cause will be conducted afterwards. In particular, to evaluate the performance of incident management, the TDX matrices are often used. TDD is the time to detect an incident from the start of its impact. TDE is the time to engage a responsible service team for incident investigation. Finally, TTM is the time to mitigate the impact of incidents. The ultimate goal of incident management is to reduce this TDX and keep SLA, that is, service level agreement. Next, I will talk about the motivation and methodology of this work. Although incident management has become highly automated and fast, we still observe significant delays in different incident management phases. It includes critical incident detection, impact scope identification, and root cause analysis, etc. Particularly, the root causes of incidents are very complicated. For example, a failure could cause incidents in multiple locations. The cause of an incident could come from multiple sources. An incident happen to a low-layer service could incur incidents in upper-layer services. We are motivated to have a clear understanding about these phenomena as well as the underlying reasons. This can provide us with important guides to build more reliable cloud systems and services. For methodology, we gain insights about incident management by studying 2 years of incident tickets at Microsoft. And incident tickets include timestamp, location, a title briefly describing the problem, and discussion conducted by engineers, etc. Particularly, we focus on 6 core services. which are data center management, network, storage, compute, database, and web service. These 6 core services are known as the fundamental basis that thousands of other services rely on. They produce a large number of instances and almost half of impactful instances at Microsoft. For study approaches, we first analyze instant tickets by calculating the distribution of instances from different angles. We then conduct face-to-face interview with engineers to understand the pain points of instant handling. Finally, to support our findings, we design validation experiments to obtain statistical evidence. In next section, I will present the characteristics of instance along multiple dimensions. The first dimension is instance severity, which is determined based on its potential customer impact. A common classification for severity is low, medium, high, and critical. For example, a high CPU usage is normally a low severity issue, but a data center power failure is likely to be a critical one. Our analysis found that low and medium instances together take up more than 19% of the total. The number of high instances dropped significantly, and critical instances account for less than 0.5%. The second dimension is instant fixing time. We define it as the summation of time to detect, time to engage, and time to mitigate. We found that compared to high instances, low and medium instances require more time for mitigation. It is because they are usually trivial issues. Engineers will not address them immediately as they often could be mitigated automatically. Regarding critical instances, they are always the most consuming ones in different services. This is because most of them only happen once. Auto mitigation will fail, and engineers will need a long time to investigate. The third dimension is instant root cause. We categorize them into 6 classes. For example, network issue, human error, deployment issue, etc. Each of them has some subcategories. Our analysis reveals that network issue with hardware and human error with code defects are the 2 dominant root causes. These 2 account for nearly 23% and more than 19% respectively. More details about the characteristics of incidents can be found in our paper. In the next couple of slides, I will introduce 2 fundamental challenges of incident management and the associated pain points. Due to the similar design of cloud systems, these challenges are actually general across different cloud vendors. The first challenge is the discovery of service and resource dependencies. Dependency is the relation that cloud applications rely on multiple services and resources to function properly. Currently, fine-grained dependencies still rely on human knowledge to build. The first problem caused by the missing dependency graph is imprecise estimation of instance impact. To understand how the impact estimation is delayed, we define time to broadcast as the time it takes to broadcast a failure to all of the impacted services. From table 4, we can see time to broadcast has comparable values with time to mitigate in almost all services, which indicates that impact estimation is indeed a challenging task. We provide a real-world instance, which shows that even the root cause is found, we still need a big picture of which and how services are impacted to prioritize the recovery of cloud resources. This leads to our first lesson learned, that is, besides root cause localization, finding all impacted services and prioritizing resource recovery are also important. The second problem of missing dependency is there will be redundant engineering efforts. That is, incidents caused by same failures are handled by different teams separately. To understand the situation of redundant effort at Microsoft, we calculate the number of instances that are redundantly handled by more than one service team. We also calculate the average number of teams involved for such instance. We can see from figure 4 that network and storage have the worst situation. Example 2 shows that the cascading effect of failures and unclear service dependencies indeed incur redundant effort. Therefore, our second lesson learned is that merging separate maintenance work from dependent teams is important for incident mitigation and effort saving. The second key challenge of incident management is resource health assessment, which consists of signal collection from cloud resources and anomaly detections based on the signals. The first problem caused due to inaccurate health assessment is flooding alarms. To know the distribution of flooding alarms, we use two kinds of incidents. The first is incidents that are marked as false positives in our system. The second is incidents that never get handled and mitigate automatically. We can see from figure A that network reports much more flooding alarms. Example 3 presents an instance showing a failure could trigger a large number of incidents, even signal aggregation have been applied, which is basically our third lesson learned. In cloud systems, more sophisticated signal aggregation strategies are still in high demand. The second problem of inaccurate health assessment is grid failures. Such failures are subtle and thus defy quick and definitive detection. To understand grid failures at cloud systems, we calculate the number of incidents whose severity level increases during their lifetime. For example, from medium to critical. This is because they are not correctly identified regarding how serious they are at the beginning. We see that network also has the large number of grid failures. We provide two examples of grid failures. In both cases, error rate reported by monitors is in a reasonable level, so the issues are mistakenly tolerated by the monitoring system. Our fourth lesson learned is that large-scale cloud systems are prone to grid failures, and there is a trade-off between flooding alarms and grid failures. After knowing the challenges, I will talk about our understanding about them from the perspective of cloud system design and operations. For the dependency issue, we think that they are essentially brought by system modular design and the visualization of physical infrastructure. Modularity design breaks the system into smaller function units, such as microservices. It, however, complicates the building and maintenance of dependencies. Recently, a new category of clouding computing services called function as a service is getting more and more popular. Such a design will further compound this issue. Meanwhile, visualization makes the dependencies dynamic and weaken geographical relationship of physical machines. For the difficulty of resource health assessment, we conclude two main reasons. The first is systems fault-tolerant property, and the second is a series of monitor design and distribution problems. Systems fault tolerance sometimes hides small issues from being discovered at the beginning. Monitor design and distribution talk about what system signals and resources should be monitored. Currently, system monitors are mainly configured in an ad hoc manner. To pursue a better design, we must consider the system as a whole. Finally, we come to our AIOps framework called BRAIN, which is an effort towards more resilient cloud services. From the framework diagram on the right, we can see BRAIN has three modules, which are data and feature, data preprocessing, and techniques. In the first module, we collect data from two sources. The first is raw instant tickets reported by 6 core services at Microsoft. We also utilize many kinds of system input signals. For example, near real-time healthy signals, near real-time metrics, system topology, etc. The second module is data preprocessing. The poor quality of instant management data is a notorious problem. Therefore, we value the step of data preprocessing. Specifically, we perform entity extraction to construct dictionaries, which can facilitate feature engineering. Feature repair helps complete missing or incorrect fields of incident tickets. Moreover, due to the large volume of signals, we also perform automatic signal selection for model training. The last module is the techniques of a brain, and we have 3 types of algorithms targeting different incident management phases. Incident detection is to identify potential patterns and detect incidents in early stage, which targets time to detect. We employ LSTM and random forest models upon a variety of system signals, and 0.7 F1 score has been made when detecting certain types of cloud failures. For example, unplanned VM reboots, node failure, etc. The next algorithm is instant auto triage. It tries to automatically find the responsible service team for instant investigation, and the target is time to engage. We use 2 neural network models called GRU and CNN and achieve a notable accuracy. Finally, instant correlation targets both time to engage and time to mitigate, which finds the relationship of incidents to understand the big picture of failures. We propose 2 methods. The first one is an event-based method, which relies on text similarity of instant tickets. The second one is a resource-guided method, which uses the common cloud resources mentioned in different instances. We refer audience to the cited paper of individual work for more details. To check the effectiveness of our framework, we collect impactful incidents reported in the past 1 year. Particularly, near 45% are engaged with BRAIN, while the remaining 55% are not. In Figure 11, we report 75th percentile of different TTX. The evaluation shows promising results of the BRAIN framework. Moreover, to account for the sample-to-sample variation, we perform a non-parametric hypothesis test. The null hypothesis is that the reduced TTX seen here is due to the randomness in the data. The key results are summarized in Table 5, where we can see all the decisions are rejected. Supported by this testing, we conclude that BRAIN's association with shorter TTX are statistically significant. To summarize our work, we first introduced the current state of incident management in production environments. Then, we conducted the first comprehensive study to provide a broad view of the key challenges of incident management. We also provide our understanding about the fundamental reasons of these challenges. Lastly, we propose an AIOps framework towards intelligent incident management and show its practical benefits conveyed to the cloud services of Microsoft. This is the end of my presentation, and thank you for your listening.